and thanks everyone for coming to listen to the talk. And as Jeff said, I've spent the bulk of my career thus far working in numerical simulation algorithms. For the most recent part of that, since I got to MIT and since I've been back, that the application of those has been in oil and gas. When I went over to the States, to MIT, I was working in civil and environmental engineering there, but we were working with the Earth Resources Laboratory on a project for them. They're a very well-established consortium over the last 30 years working in oil and gas. And what they got us in for was to help solve some of the problems, the multi-physics problems that they were having in oil and gas. So there's traditional simulation techniques that are used for these problems. But those type of traditional techniques weren't appropriate for the more complex problems that are turning up in this industry. And those problems involve different fluid flows and gases and electrochemical problems and things like that. So the idea was to come and develop new techniques. And so we worked on that there and we continue to work on that. And I'll talk a little bit about that today. But before... Wait. Why not? Yeah, I'm not entirely sure. I asked about that earlier. Let's just try this again. There we go, now we're working. Okay, so before we get into any of the simulation stuff, what we first have to do is work out what the state of play with oil and gas is to try and motivate why we might need simulation for this stuff. So obviously everyone's pretty familiar with how infused in our society oil and gas is, particularly oil. Our entire food supply chain completely relies on it. If oil went away tomorrow, so does food. But plenty of other things, so all of our freight, goods and everything we like to go to the shop and buy, all of our long distance travel and all of our short distance travel as well, our commuter cars getting to and from work and everything like that. So these are the standard things that everyone understands rely on oil. There are plenty of less obvious things where oil is infused in our society and would actually have a major impact if it went away. Coal. We're told that Australia potentially has somewhere in the order of maybe 300 years worth of coal supply in the ground at the moment that will supply our electricity needs. And that's fantastic, and we think that means we have at least 300 years of electricity. But if you look at the coal supply chain, then just about every aspect of that is actually reliant on oil, reliant on fuel. So from getting the stuff out of the ground to actually getting the stuff to the power station to perhaps getting it to different countries and different places through shipping to actually sell it and get a bit of money into our economy, everything relies on oil. So while we've got this terrific coal resource, without oil it doesn't actually serve any purpose whatsoever. And there's plenty of other industries where it's just as infused and just as important to maintain that industry. And that's one of the major reasons that so many governments, and the US government particularly, treat oil and gas as a national security issue. All right? It's not just a resource issue, it's a national security issue. Firstly, because if it goes away, your entire nation falls to pieces. And secondly, because nations are very willing to fight wars over this. And so that becomes very important and much more important than perhaps we'd like it to be. All right. And if oil did go away tomorrow, then perhaps the world would plunge into something that may resemble your post-apocalyptic type movies and TV shows where effectively you have no electricity, no food, no transport, really very little of anything. So what's the answer? And I wholeheartedly believe that renewables are the answer, which is a bit weird to say given that I'm giving a presentation on oil. But I'm a pragmatist, and really oil is a finite resource. Oil is basically just a really dense way of storing the sun's energy, as is coal. So really we're using the sun as it is, it's just that it's not renewable. So what we need to do is come up with battery tech and things like that is comparable in its storage capacity to these type of fossil fuels. But the sorts of technologies that these renewables can run really aren't there yet. They're certainly in no state to replace our transport system. We've got a few solar panels on roofs and things, and that's great, but there's absolutely no way that if oil ran out in the next couple of years, that they would actually replace our transport system. What are other alternatives? If oil ran out tomorrow, maybe we could revert back to steam. We certainly have plenty of coal, so maybe steam's it. I don't see us going backwards, but maybe that's the case. And nuclear is certainly an alternative to coal and oil and things like that, but I'm not sure that we're all going to be driving around in time traveling DeLoreans anytime soon. So really, oil is what's got to get us to that renewable future. And we have to make the resources that we have last as long as it's humanly possible, such that we can get to the renewable future and no longer be reliant on that oil. And fortunately, the reality of it is that oil isn't going to run out tomorrow. So we have oil, but what's actually going to happen is that the oil is going to slowly run out, and the prices of oil are going to get to a point where it's completely impractical to continue using it. And that's part of what we need to do. We need to be able to recover this stuff in a much more efficient, cost-effective way, and I'll talk more about that. This diagram here is from the BP Statistical Review. They run one of these every year, basically working out how much oil production occurs and consumption and things like this. And this is for our region. This is Southeast Asian oil producers. And this is stats, so this is your total oil production, and this is your total oil consumption for our region. And you can see that based on this curve, and this is a fairly well understood curve, and this curve will continue down like this, not dissimilar to a distribution type curve. We've already reached peak oil for our region. We've reached peak oil somewhere around 2000, and this curve is now in what's called a critical decline, and it will only continue to go down. Now this is a problem not only because we're running out of oil, but because our consumption of oil is increasing markedly for a region. This is just Southeast Asia, not China or anything like that. And this is the Australian proportion here. And if you look closely on this graph, according to BP, Australia production this year was somewhere in the order of 400,000 barrels per day. And Australian consumption was somewhere in the order of over a million barrels per day. So we're over a factor of 2 using rather than reducing. And so we have to get our oil from somewhere else. And so it depends on everywhere else to be producing oil. Now, this is a similar plot, but this plot is of global oil production. And it's widely understood that we're here. We are at peak oil currently. And from here on in, global oil production is expected to decline. And as oil production goes down, the oil price goes up, potentially exponentially over the next 10 to 20 years. And that can be a huge problem. Now, the other thing about this plot here is that where peak oil occurs actually also coincides with the peak of cheap oil, all right? Cheap and easy oil. And that's what we've been producing thus far. And by cheap oil, we're talking about oil reserves that are very, very large, and they're located onshore, and they're easy to get to, relatively easy to find. And it's good quality, light oil, and it's very inexpensive to produce, of the order of $1 to maybe $10 a barrel. The sorts of stuff they produce in Saudi Arabia is about $2 a barrel. So it's cheap stuff to get out of the ground and then on sell, very, very easy. Now, with this decline, not only is that less oil being produced, but that oil is being produced from much more difficult places. It's much harder and unconventional oil, potentially far offshore or scattered in very small reservoirs all over the place, politically difficult or dangerous, hazardous places. And it's also heavy oil, and it can be very expensive, $80 plus. And this isn't in 10 years it'll be $80 plus. Plenty of production currently depends on the oil price, because when the oil price is at 80, there's a lot of operations that shut down because they're producing at about that. When the oil price is at 120 or thereabouts, they start back up again and they can produce because they can actually make a profit on that. So this isn't a distant future reality. This is currently, there is oil being produced at this in these difficult places. And so you're talking of perhaps an order of 80 times the price. And so when we look at the price here, we're talking in cents, so $1.60. But conceivably, if all of the oil that we're getting is sort of 80-fold that to actually produce, then you might be actually looking at those figures being dollars rather than cents. And obviously no one's going to be driving around very much if that's the case. So we need to do something about this. And we need to actually work out how to get the oil out of these difficult places in a much more efficient and easy manner. Or we need to make the most of our existing resources to make them last as long as humanly possible. And like I said, if we're putting solar panels on the roofs, that's great, but this technology isn't going to replace oil anytime soon, so we need to actually be able to do something in the meantime until hopefully enough investment in this technology gets us to a point where we can replace oil. And what I'm here to say today is, as I believe and as plenty of others do, is that simulation is the answer. Largely what's happening with these really difficult resources is that we don't understand the physics well. We don't understand the processes well, and we don't have the tools to be able to develop recovery technologies accurately enough to be able to get this stuff in a cost-effective way. And as with many aspects of engineering, oftentimes we use simulation to solve these type of problems, and I and many others believe that simulation is one aspect that can help in this problem. So, if simulation is the key, it's worthwhile to work out where simulation might value add. And I'll talk for a little bit on a couple of unconventional liquid fossil fuels, the sorts of difficult oils that I was talking about a second ago, some experiences that I've had, some areas that we're working in, and some potential areas, certainly region-specific in this. So, unconventional liquid fossil fuels. Firstly, on this block, we have some conventional non-associated gas. So these gases and some conventional oil and associated gas. Wherever you've got oil, you probably have some sort of gas resource. It's like your jerry can. You've got fuel and then fumes. It's a similar sort of thing in the ground. So this is your conventional resource. This is in nice, porous rock. You can pump it out of the rock. You can do various things to recover it. And then you have non-conventional type things like shale. Now, shale is similar sort of rock, but you have a much thicker tar-like consistency of the oil in that region, or in that geological structure. And to actually recover that, the way that it's done is you actually mine the stuff. You mine it, you get it to the surface, and you then process it and get the oil out, because there's no way you can pump this stuff out of the ground. So just that process alone is very costly. There are other processes you can heat it up and various other things underground, but none of those are particularly viable at this point in time. Additionally, we've got coal bed methane or coal seam gas, the sorts of things that we're hearing a lot about in our region, and I'll talk a little bit about that. But once again, it's not just a simple process, and there are also a lot of perhaps environmental impacts and social impacts and things like that need to be considered and improved upon. And then there's other types of non-conventional oil that's not on this figure, but things like offshore drilling and deep water drilling, which can be very costly, and I'll talk about that. And also things like tar sands. And Canada is an area that has a lot of tar sands deposits. And again, you mine that and extract the oil from the actual rock rather than pumping it out. Alright, so I was actually at MIT in the States when the Gulf oil crisis occurred. This is the Deep Horizon oil rig, and obviously everyone saw on the news that had a major explosion, and then there was a huge oil leak that was associated with that. And we consulted a little bit with the US government on this, as did just about everyone else in the entire country who worked in oil and gas, because they had a lot of problems trying to actually get this leak to shut. The leak itself was there for 87 days. It was leaking straight into the ocean for 87 days, and they were trying to work out how to stop that leak. And so they were talking to everyone, and we tried to apply a little bit of our modelling to some of the problems, but it wasn't in a time frame that was really going to solve that problem. It was more thinking towards the future. But the problem itself, just before we talk about the simulation, what actually caused this was that this rig was drilling. This rig was a very, very special rig. It was basically the most advanced oil rig in the world at the time, and may still be, its sister rigs. It, several months before, had just broken the world record for the deepest water to ever drill an oil well in. So this was a transportable well. It was basically floating, and it would go around and drill the wells, and then you get another rig in and tap them and get the oil out. So it was pure purpose was to drill. And several months earlier, it actually drilled a well in 10.5 kilometres of water. So that's what we mean by difficult oil. You drill an oil well in 10.5 kilometres of water, you've got some serious challenges involved. So that was 2 months before. This actual incident happened in 1.25 kilometres of water. So it was much shallower by comparison, but this is still classified as very difficult oil because it's so deep. What happened was they were drilling through and they actually reached a gas deposit, and that gas deposit is called a bump, and it shot up the drill pipe. Now there are fail-safe mechanisms on the sea bottom to try and catch that, and they're well tested and used extensively throughout the industry. Now the problem was, and the reason that BP got raked over the coals so significantly was because there were several neglect issues. That mechanism had a malfunction 4 weeks earlier, and they hadn't actually properly fixed it. The console that operated that fail-safe was having issues before that stage, and so all of these things came together such that when that gas was hit and it ran up the pipe, it wasn't stopped, it made it all the way to the platform, and then there was just gas leaking out. That gas got sucked into the engines on the platform, the engines started whirring up, and there was an explosion. And in the initial explosion, in the explosion of the fire that ensued, 11 people were killed. Another 60, I think, got off the platform, and then they had this problem of trying to put the fire out. And so they got these fire ships in and flooded it with water. And what actually happened was, because of the floating platform, you just filled it up with water, the thing sunk. And you have 1.25 kilometres of steel pipe that bent over, split, oil comes out. So that was a major problem. It was a response issue, all sorts of legislation and things that should be stopping this kind of procedure. There's uncertain as to whether the thing would have burned itself and sunk anyway, but certainly the water that they put on it was a factor. Now when that thing broke, now you've got 1.25 kilometres of water to find some submarines that'll actually get down that depth, and that took them plenty of time. And you've got this, and this is your oil leaching straight out into the ocean, and it did this for 87 days. Alright, so that's obviously a huge concern, and now they're in disaster control mode and working out how the heck do you stop this stuff coming out into the ocean. And it's not as simple as just putting a plug down. There's far more complicated stuff. You can see the amount of machinery down there. It's a broken pipe that they have to cut out of the way. You've got to get subs that are capable of doing it. You've got to manufacture things that are capable of doing it. All sorts of things. Now, this is going to work. The next video is something that they came up with quite a few weeks into it. This is a cap, and basically this is a big funnel, and then it sucks the oil up above that, and they put this on top of that. And this is where they were having some major dramas and where simulation really could have helped them if we had some multi-physics, next generation type simulation technologies. The problem with this is the oil's flying out, and in that deep an ocean, you've got very high pressure and very low temperatures, and you've got methane coming out as well as oil, as well as other chemicals. And what was happening was they put this cap over and it served the purpose for a little while, but it would ice over, and then the oil would come out anyway. And so they had to keep doing this and doing all sorts of things, trying to make this effective. And this was only ever a quick fix, because the way they actually plugged this was to drill another well adjacent to it, go horizontally, meet up with it down below there, inject it with concrete, and cap it that way. And they actually had to try that a couple of times as well, I seem to remember. So this is why it took 87 days to get this thing capped and finished. Now, as I said, 11 lives were lost. The environmental impact was huge, and 780 million litres of oil spilled into the Gulf. All right? And the environmental impact of that being a slip would have been significant. So one of the first things that they were doing was going down to the bottom and actually injecting dispersants into that oil. Dispersants are used for oil slicks on the surface because it breaks up the oil, and then bacteria get to eat it and basically break it down, and you don't have that slick problem. So they thought they'd inject that down right at the leak. The problem was what they then had was these massive plumes of dispersed oil with bacteria eating up all the oxygen in that and floating around. And so you get a school of fish or whatever floating through that, and they'd all suffocate. So here's another whole problem that they've got. From trying to fix a problem, they've caused another problem that they didn't understand for a while. And so what they needed to do was then have these ocean models modelling this stuff, moving around to work out where it's going to go and what sort of impact it's going to have. And the ocean models weren't capable of modelling this type of fluid either. So that's another area of future numerical simulation that for this type of crisis in the future really needs to be investigated. Now hopefully we don't have a crisis like this in the future, but if you have those tools in place that you're already using for other things, it becomes much better for this sort of thing. The economic impact is obviously the major thing as far as BP was concerned. $42.2 billion. That's in fines and in litigation that they paid, and that's not including their company's losses. That's purely what they had to pay to others as a result of this. And you can think, probably count on one hand the number of companies in the world that can cope with a cost that large. Now, this drill rig itself was $500 million. They were paying $1 million a day to actually do that drilling, and they took several months to do it. The reserve that they have now written off because this happened there, that reservoir was probably going to produce 10 to 20 years of oil. So if that's how much oil comes out of it in 87 days, think how much oil comes out of it in 10, 15, 20 years. So that economic impact isn't taken into consideration in this number either. So we've got a very serious issue all going on here. And these are the types of social, environmental and economic impact that these next generation or difficult oil and gas types of reserves really pose. And we need to be able to work around that and hopefully mitigate that, because many more of these in BP won't be here anymore. And probably these offshore types of drilling probably won't be there for a while either. Alright, so that's offshore, and offshore is a very complex system. We've got a lot of these systems closer to home, and coal seam gas is a very divisive issue, and a lot of the problems around coal seam gas are that, at least the perception amongst the general public is that we don't understand the physics very well. We just dig in, the stuff comes out, and hope for the best. So obviously, as I've been saying, if we have simulations that can actually tell us more about what's going on, hopefully we can improve that perception as well as the actual fundamental physics and understanding behind it. Now, the way that coal seam gas works, it's obviously different to oil. We've got your coal, and in micropores in the actual rock itself, you've got methane, and that methane sits there, and that methane is held there from the pressure of the water above it, the water table. And so the way that the conventional way is you drill, you start pumping out the water table, which gives you a drop in the water table in the general region. The drop in pressure means that the actual gas comes out of the coal and runs through these cleats, and then you recover it. And so what you've got to deal with is you've got this contaminated water that you've got to be the largest in the world. Now Canada, or Alberta in Canada, is sitting on about 175 billion barrels worth of oil. And so that's actually pretty competitive to Saudi Arabia, you've got to admit. But what that oil is actually sitting mostly in that tar sands, very thick, very difficult to recover type of material. The way that they get most of it out is to actually mine it, like I said, and to process it, but you can only mine about 3% of the reserve. So you've got 97% of the stuff that can't be mined that has to be or could be recovered via some means. And the way that the most commonly thought way to get this stuff out is steam-assisted gravity drainage. And the idea is that you drill these wells, not dissimilar to what you would with oil. However, you drill two horizontally. This stuff is very thick, but if you can heat it up, the viscosity drops and it will actually flow. So what they do is, once it's actually producing this top one, you inject steam, it heats up the general vicinity, it lowers the viscosity of the stuff and it drains down, and then you pump it out the bottom one. But there's a lot of multi-physics things going on here that they really don't understand. You've got steam, that steam will then condense, and you've got water. You've got probably water or brine in the shale already. You've got, sorry, not the shale, the tar sands. You've got obviously the oil that's got to travel out. That oil's changing in viscosity. You've got thermal properties of everything. You've got these two wells that are a certain distance apart, the rock properties that are a certain type of property. All of this stuff is all happening simultaneously, and it's very difficult to understand what the best practice of doing this is. Additionally, it might cost you $1 million or more to drill an experimental one of these. And they've done a couple, but that's where it about sits. one or two of these they've done experimentally. Because what you really like to do is optimise the distance between these and what pressure you pump the steam in, and what temperature you start to pump the steam in, and all that kind of stuff. Because once the steam condenses, that water can actually block off the path of the oil as it travels through, and all of this stuff's happening simultaneously. And this is the exact type of problem that we hope to simulate with the molten physics simulator we're developing, and I've got one of my guys working on that currently. So these are the sorts of problems. They're really big problems, but if you can solve them, then perhaps a fair proportion of the 175 billion barrels becomes available, which starts to mitigate those, those dropping off plots that I showed earlier. All right, so that's just a little bit of the future of, let's say, unconventional oil, and where simulation might add or value add to that to try and lower the price, increase the amount of recovery. But certainly there are a lot of things that simulation can do to current conventional oil as well. Obviously these type of oils haven't gone away. We've got reservoirs that we'll be producing into the next couple of decades, so if we can get the most out of those reservoirs, we're enhancing our position as well. Now, if you've got a reservoir here, what we're really interested in when you're producing is the properties of the rock. And we've got some techniques from the surface, but basically you're looking through a couple of kilometres of rock to look at a slightly different rock and work out whether there's oil there or not, which is not particularly easy. So the easiest way is to actually drill core samples. And if there's oil there, that's great. And the other thing we get from core samples is the actual property of the rock, because we want to know how easily fluids flow in the rock, because that tells us where to put wells and that kind of thing. This is a micro CT scan of a cross-section of, I think this one's Berea sandstone. This is a bit of a core sample about that large. So you can see that where the oil actually lives isn't in these giant big caves underground. The oil is actually infused into these rocks. And the way that the oil moves is through the pore throats between these little pores. And this black is oil, grey is rock, white is empty. And so you have this kind of configuration across many kilometres of these reservoirs. If it's a big reservoir in Saudi Arabia, you might be talking of tens of kilometres or more. And the way that the material or the oil actually flows can be different to depending on where you are throughout that reservoir. And so you actually have to manage how you recover that oil based on it. And you don't ever just drill one, unless it's a very small reservoir, you don't drill one well and just pump it out. It doesn't work like that. What you actually do is drill many wells in certain places, and you might also, or most commonly, you would drill other injection wells and pump water and gas and things to actually try and move the oil closer to your recovery points as well. So we need to actually work out where these need to go, and how much we pump in and what type of fluid we pump in and all that kind of stuff. So what we do is we measure the permeability of these core samples, and that gives us data points in various places, not many places mind you. And then we run these field scale models, and this is a tried and tested technique been used for the last 30 years. This is an old type of simulation field scale model. But basically, you've got pumping stations, your injection stations, and your recovery stations and things like that. You move these around and optimise them and work out where the most oil actually comes out. The properties for this model come from your core samples, and you might have, in this case, you might have maybe 10 or 20 or more core samples that give you a few data points. This is the more modern approach and the types of simulation that people like Halliburton and Schlumberger and the likes are doing. So you've got multiple reservoirs, multiple types of simulation engines all solving on top of each other and telling you different things. And you've got all your different injections and production wells all in different places, and you might spend a year or more, a team of engineers spending a year or more optimising where these all go to actually get the most out of the reservoir. Now once you've done all of this absolutely new age, space age type oil recovery stuff, obviously you want to make sure you get the most out of the ground. Now primary recovery, if we just drill a hole and pump 5 to 15% of what's originally there, that's what we can get out optimistically. Secondary recovery, which is what I was talking about with pumping water and gas and things like that, and actually pushing the oil to the recovery points, an extra 30%. And then there's this tertiary recovery techniques, which is kind of the new age stuff, which is maybe you heat the stuff up, maybe you add even chemicals and surfactants to change the properties of the fluids and try and get as much out as possible. Might add 5 to 15%. And the conclusion of that is that basically currently we're leaving between 40 and 60% of the oil in the ground using current, absolutely modern techniques. Roughly half of the oil is left in the ground and we walk away from it because we can't recover it using current techniques. So even if we just optimise these tertiary recoveries, at the moment they're really ad hoc and hit and miss, and if it worked before, it doesn't necessarily mean it's going to work now, and it doesn't necessarily mean it's not going to work next time. So they just use techniques that they've used before. But if we can customise these for a specific reservoir, that could add several percent on this recovery. And several percent across all of the resources around the world, you're talking a matter of maybe a decade extra oil. And so that's a pretty significant thing, and that's the holy grail of this oil research, to increase that percentage. Now, one thing that we're working on is increasing the resolution of those field scale models. So I was saying that we're taking core samples, and basically that's the only data that we have for the actual flow properties. You run flow experiments. So you take your core sample, put it in a machine, flow a bunch of fluids through it, and that'll tell you what your permeability, your relative permeability is. You use that for your field scale, and on you go with the management of the reservoir and production. What digital rock is the next generation of that. The idea that we have very few data points from these core samples. So we want to actually increase our resolution in that field scale model. We increase our resolution on that, it means we can have a much more optimum management of the reservoir. So the idea is you take rock, so for example a core sample, you do a micro CT scan of that rock, you reproduce a 3D digital image of that, and then you use that 3D digital image to run simulations on it. And those simulations will actually tell you what the permeability, the relative permeability, if you set them up correctly. And you can use that information in exactly the same way as you used your experiment initially, and put it into this field scale model, and on you go. Now, if you're just taking it from core samples, you've got the same number of data points, and it doesn't really help you, aside from the fact that it's probably a lot cheaper than the flow experiments that you would do. But the idea is that we don't need a perfectly intact core sample. For the experiments, it needs to be, perfectly cylindrical and be able to put high pressure fluids through it. For this technique, we just need to take a scan of a bit of rock. And that bit of rock can come from anywhere. It can come from drill spoil. So as you're actually drilling a reservoir, you can recover a lot of that drill spoil and perhaps use that. It could come from actual sensors on the tip. Currently, drill heads have an array of sensors that tell it where it is as it snakes through a reservoir. Ultrasonic and any number of NMR and different type techniques. So it's not out of the realms of possibility that you might actually put some form of micro CT scanner into the future on one of those drill tips and get real-time data on what the rock looks like. And if you can get these simulation engines to work quick enough, you can get real-time data on what the permeability is as well. And so now you're talking a matter of millions of data points rather than tens or hundreds of data points, which is a really big advantage when you're doing this field scale stuff. So this is what we've been working on. This is largely what I work on at MIT, what I continue to work on, and there's a couple of other companies working in this field as well, and actually consulting with industry currently. Now what we intend to bring to the table is that our methods are somewhat more accurate than or we intend them to be more robust and more accurate than what's currently being used. Currently, grid-based methods are being used, and we're using a more advanced technique that hopefully what we'll bring to the table is greater accuracy. And that method is called smooth particle hydrodynamics. So basically, we've got many particles in space. Those particles you basically represent your fluids, your oils, your waters, your rock, things like that as particles. Not dissimilar to how water has molecules and those molecules react with each other, it's just on a larger scale. And the potential between those particles, or the forces between those particles, are scaled based on a potential relationship. Again, similar to a molecular analogy, but on a larger scale. And so we model a lot of things for these particles, and the advantage of that is that multi-phase and interfaces are much easier. You can impose all sorts of physics on these. You don't just have to have Navier-Stokes fluid equations. You can do electrochemical things. You can do transport and solutes and all sorts of different things. And so that's the intent and the future of this that we're working on. Additionally, phase change, one of these particles can go from being a fluid to being a gas and back to a fluid if you set up the equations to state and the properties right. And that's all of the types of things that we're working on currently. The current stuff that we're working on is around accuracy and that multi-physics, but this is some of the previous stuff we did, just the pretty picture work. This is just a water droplet splashing. You can see that this is handling that free surface flow very easily and splashing around and doing its thing. This next one is Rayleigh-Taylor instability, which is oil on the bottom, water on the top. Oil rushes to the surface under gravity. And you can see the sheer number of interfaces that are very difficult to handle with other grid-based techniques. And this technique takes no more numerical solution time for many interfaces than if this was just a single phase.
How many particles you got there?
This one is 1 million particles.
Cube.
1 million particles in the cube. So it's, resolution on this is reasonably good. We've gone up to 60 million particles for one of our reservoir solutions, and that took up about 20 gig of memory in the computer. Now, the other aspect of this is that the parallel processing is critical, and we spent a bulk of our time getting the parallel processing right, because the only way you're going to handle multi-physics is to actually have computers to be able to deal with that. But something that's a little bit more pertinent to the oil, this is just a 2D example just for illustration purposes, but is the actual surface tension and the phase behaviour. So in this case, we've got water trying to flush out the red oil and rocks, and we're dealing with different capillary forces here. So in this circumstance, the rock is oil wet, so that means the rock wants to stick to the oil, and the water just zips past, and it doesn't really do a whole heck of a lot. Whereas on the next example, the rock is water wet, and the water wants to actually wrap around these particles. Now, the reason that this is important is this is exactly what surfactants do. So surfactants are to program the different capillary forces of the fluids in a reservoir. And if you can tune the fluids in a reservoir such that the water wets the rocks and pushes all of the oil out, ordinarily rocks are water wet anyway, but if you can program it such that the capillary forces of the water in the gaps and things like that don't block the oil, then you can actually get a lot more oil out. So the intent for this simulator into the future is if we can actually put chemical reaction into that, then we can look at how a surfactant gets travelled through a certain rock structure and how that surfactant actually changes the, let's say, permeability or relative permeability of the fluid, and then make an assessment as to whether that's the right or wrong surfactant for the job. And so that speaks to the tertiary recovery stuff I was talking about before, how it's hit and miss. This type of simulation technology can actually enhance that, improve that, give us a better understanding of what's going on. But we need to develop it, and we need the big computers to actually run it on. This is just a 3D version of that. So obviously it's very porous, so most of the water flushes out the oil. You can't really see it very well in this light, but you get the general gist. So those are some of the previous simulations that we've done, and we've now moved on from that, and we're trying to implement all of these different multi-physics capabilities that I've been talking about. And that's a relatively slow process, and we need to do a lot of verification work, because the more complex you get, the more difficult it is to prove that you're accurate. So we need to tick all of the boxes all the way along, and that's what we're doing currently. And the hope is that if we develop these multi-physics capable engines, that we can actually model all of these, the current oil reservoirs and onto the future and difficult reservoirs and resources, and actually get more of that stuff out. And maybe instead of that production dropping off, we can start to plateau it, or potentially that if it still does drop off, we can keep the price at least low enough to get us towards that renewable future that I was talking about, and with any luck, keep us on the road for at least our lifetimes. All right, thank you very much.